Good morning, students. Today we are going to learn the Newton's laws of motion, but in a slightly different way, which is generally escaped by many books and many lectures, what we have already seen or uh, found. But this lecture actually is made to introduce those particular concepts which can help you to solve the numericals or any kind of conceptual problem very easily without making them very complicated. Okay, so let me start from the very beginning. So Newton's first law is telling that if there are no force from on a body, external force on a body, if there are no external forces on applied on a particular body, right? So uh, the state of the motion remains unchanged. So now I'm going to write. So So here I have to mention many things. Here, first, the here the force we are talking about. Okay, the force we are going to talking about is the external force. Okay, so Newton's laws are not bothering about the internal force uh, among the matters or the system of the particles. So the force which are applied externally on the various uh, system of the particles, so it is applied on the one particle. So we are bothering about those forces. So it is telling the total force. If the force, external force is not applied, that is, it is made zero, then the state of the motion is unchanged. So it remains unchanged. So that is very important. But how can we decide the state of the motion? For example, here is I have drawn two planets. One is static, say, almost static. So forget the part of that how can it be static or it is moving. So forget that part. I'm not bothering about those particular case. But now I'm picking a static one kind of static planet, and a planet is revolving around some star. Okay, so here is a star. So around a planet is so this is the planet number one, T1, and this is the planet number two, which is revolving around a star. Suppose we were standing on this planet here. Okay, so it is not non-rotating object, even it is not rotating axially. Okay, and another person is here. So, so you are the first observer, one, and this is the observer two. Suppose there is an object is placed on the surface of the planet one, and observer two, and now we are going to analyze that what are the state of the motion observed by the O1 and O2. That's all. So if I will see, if I consider the only O1, the observer, right? Then we will say that the object is moving. Object is not moving, right? Because it is static. Both are static. So this is static with respect to, so the object, I'm going to write, so object is static with respect to observer 1. Static means its velocity is 0. What will be happened, what the observer 2 will see? Since he is rotating around the star, he or she will see this object is also rotating, right? With you. That is O1. And seeing any rotational motion is the accelerated motion. You know that. That means this object is appeared to be accelerated with respect to O2. So even there is no external force acting on this object, any force acting on the object, right? This observer 2 will see this particular object is being accelerated. So for O2, for observer 2, the object is accelerated. So how is it possible? Okay, so I can pick another observer, O3, here say, who is moving uh, with a spaceship with a constant velocity. So he or she will see that the object is moving backwards with the same velocity, right? With you. So that means this observer O3 will see that for O3, the object is moving with constant velocity. So now we are being, I think we are facing puzzle. So the Newton's law is telling the external, if the external force is zero, state of the motion is constant. So for you, there is no external force. That's why the motion remains unchanged. But for the other two observers, for example, O2, the object is itself accelerated. And for O3, the object is moving with a constant velocity. So who will decide what is the state of the motion? So answer is, so the first law our general notion is the first law is giving us the notion of the force. So it's not at all. Okay, so it is not at all giving us the notion of the force. The first law is telling us who is the observer. So in our universe, so there can be many observers, right? Like a body moving with acceleration, a body moving with a constant velocity, or on another person moving static or remain static with the body. So there are many observers, right? We can choose. So Newton first law is actually telling us who is the observer. So he means that Newton was giving us the prescription. So decide who will be or who is the observer. So there are many observers. So I am just picking everyone here. Say there are many. So this is a long list. So Newton is telling that you will pick those observers. Suppose it is a set of observer, you will pick those observers from the set who will tell the if the external force, if the total external force I should write, total external force equal to zero, that means the state of the motion unstable. So that is the very important thing. So Newton's law, the first law is motivated to bring those observers into picture who will tell that if the total external force on the body is zero, the state of the motion remains unchanged. So first law is giving us the notion of the observers. And those observer has a name. Those are called inertial observer. And the coordinate system they are using are called the inertial reference frame. So we have decided who is the observer, and now who is the observer? So observers are inertial observers, And the coordinate system they are using is inertial reference frame. And they will tell us the Newton's law, the first law. No, so no one else. So we will exclude the observer, other observers from this picture from the very beginning of the Newton's law, who will not tell or who can't tell that the total external, if the total external force is zero, the state of the motion remains unchanged. Okay, so those observers are excluded from the picture. So we have to pick those who will tell these two conclusions, right? So these are the first very important concept we have to remember. Second, here the external force has some different meaning. I have to say that here the external force means the total external force. What is the meaning of total? Suppose a body, any body, anything can be acted by many forces externally. Suppose F1, F2, F3, F4, like this, F5. See, it's the sum of the forces we are talking about. That is the I1 to F. So we are talking about actually this force in the Newton's law. So here the F external means the total external force. Why I am telling this? Because if the total external force is zero, that does not mean that there is no external force acting on the body. So there are many external forces can act on the body, but the sum of the forces, sum of the external forces is zero. That is very important. So we are talking about the resultant. So that this external force is the resultant of the all external force. So the for the inertial observers, if the total external force or the resultant external force is zero, then the state of the motion remains unchanged. So that is very important. Okay. So from the very beginning, we have picked those observers from the universe who are called inertial observers. So we will not actually move in any other way. So we will move with the inertial observers, and all the laws will be set by those observers, nobody else. Okay. So conclusion is the Newton's first law of motion is giving me the inertial observers. This is the first thing we have to remember. And please remember also, if you can write the equation observed by the inertial observer, the problem is solved 99%. You do not have to bring the pseudo force or other forces in picture. So that is why I am telling this in this lecture. So you have to bring the inertial observer into picture, and that will solve your problem very easily. Next, we are moving right now to go through the second law of motion. That is very important. That is actually the base of our physics. Starting so second law of motion. The second law of motion. What is the second law of motion? Second law of motion is telling us again the observer for inertial observer. For inertial observers, for those observers, now Newton is giving us the amount, the quantification of the force. That is how we can calculate the force. He is telling that when the total external force is acting on the body, now the state of motion is changed, right? And the state of motion, this change can be measured by the change of linear momentum. And linear momentum is the definition of the linear momentum is the P is mass into velocity. Okay. But we have to remember this velocity is instantaneous. It is not any velocity. It is instantaneous velocity. So the external force, this external force, the total external force we are talking about, the resultant one, and the observer is this equation is writing by those observers who are inertial observer. So this F external force is simple the rate of change of momentum. It is not the law. The statement, the real statement is it is directly proportional to the rate of change of the linear momentum. Okay, but again, I have to pause here to make you aware of the fact that this momentum is also the total resultant momentum. What is the meaning of the resultant momentum? It means you can consider the many particles simultaneously who are moving and the total external forces acting on those particles. Then, so each particle can move in different directions due to the application of the force, right? So suppose the momentum is P, P2, P3, P4, P5, say, and P6, say. Okay. So this P is actually the total sum of those momentum vectorially. That means this is the total momentum we are talking about. This is a uh, shorthand symbol to represent the total momentum, right? Pi. So now we have to bring the constant, proportionality constant. So that F external is equal to K dPdt and K ddt, that is Pi. So we have to study the Newton's law in this manner to remember all the things better, a clear way. So total external force must be equal to the proportionality constant K into ddt of the total momentum. Okay. So one more thing that then we actually generally remove the k in the sense that we generally fix the value of the k. It is our word, our claim that the k is 1. We make k equal to 1, fixing the unit of the Newton's law. Sorry, fixing the unit of the external force. Okay. So let us, how can I fix the unit? We claim the force which generate the rate of change of momentum, the external force, the total external force, which generates the rate of change of linear momentum unit, that is one. This force is called 1 unit force. So 1 unit force is defined which generate the rate of change of momentum by 1 unit. That means if dPdt, so if the rate of change of momentum is 1 unit, this is caused by the external force which is 1 unit. So one unit force is generated. This one unit force will generate the rate of change of momentum as one unit. So that's why the K is becoming one. So now this law becomes a simple equation. The total external force is equal to dPdt. And here P, you have to remember it is a total P. Okay. If the system of particles are now considered, it is a total P. And this force is total F, total external forces acting on the. So it is a resultant of the external forces acting on the particles or system of the particles. Okay. So I'm not willing to go further from this equation because you know after that what will be happen. Uh, So you have to write the P in the place of P equal to MV. It is a standard procedure and you can find all the steps in every book or in the lecture. But my intention was to give you the particular notions. What are the meaning of the external force in this equation? And how can I fix the value of the K? And what is the meaning of the fixing? What is the meaning of the fixing of the value of K? So these are, and what are the role of the inertial observers here? One more thing I have to tell here that this force, this equation has some limitations. The limitation is this is not applicable for those particles whose velocity is very near. So it is very v is so this is not applicable for those particles who have the velocities very near the velocity of light. So if v the velocity is comparable to the speed of light, see in vacuum we cannot apply this Newton's law. So this equation cannot be applied. So here is a hidden assumption. The velocities of the particle is very less than c. Okay. So you have to remember this also. So conclusion is that for the inertial observer, for any inertial observer, when the force is acting on a particle, the total external force acting on the particle, that can be given by simple dPdt. But only for the inertial observer this equation can be made. Otherwise, we cannot write this equation. So we will see that. And I have also shown that in some lecture that is called pseudoforce in my channel. You can visit that. I will give the link here. Okay, so we cannot for other observers we cannot write this equation very simply. Yep. Now we move to the third part, and that is a very interesting case because without any person in our world who does study physics or doesn't can actually tell the Newton third law of motion very easily. But it is often misinterpreted by many books and many lectures I have found. So it is telling every action has same and opposite reaction. That means if a body is, and again, this particular law is told only by those observers who are inertial observers. Yes. So here, if a body is exerted by many forces externally, this is the action. the body actually gives the opposite force, right? And this is the reaction. I think everybody will agree with this, so there is no problem. But here we have to remember one more thing. This is not at all actually, this is not at all actually coming from the Newton's third law of motion. So third law is telling us that action and the reaction constitute a system. What is the meaning of this statement? So it is telling that whenever the action is present, reaction is also. That means reaction action is a particular force acting on this body, but is the reaction is the force acting on the another body given by this object on which the force is applied, right? Again, I am telling. So suppose the force this F is acting on this body. So this is the body, and this body will exert in its response and another same amount of the force acting on another body, right? This force must be acted on another body. So you have to bring another body in the picture who will or who is giving the force on this body. Otherwise, there is no meaning of the reaction force, right? So reaction force must be acted on some body, some another object. So this that is why this law is not telling about the action reaction force. Actually, it is telling that we have to consider a two body reactions always, two body interactions. So it is about the two body interactions. It is not about the one body interaction, right? It is telling us the two body interactions. So again, I am going to explain that if a force is acting on a body, the body in response will accept the same and opposite force. But the opposite force acting on what? Acting on another body. Otherwise, there is no meaning of this response force, right? The reaction force. That means we have to consider two body in this at once. The body number one, which is giving the force on the body number two, and body number two is giving the response force, that is the reaction force to body number one. So you have to bring the two body into the picture to consider the action reaction forces because the action and reaction forces act on different bodies. So that means the third law actually telling us are two body interactions. That means whenever we are going to consider the interaction between the various objects, we have to consider the two body interaction first. Okay, so this is very, very important concept we have just gained, right? So it is the statement, surprisingly, I do not know it is actually historically given by Isaac Newton, but the thing is that every action has same and opposite reaction does not, it is nothing about the action reaction force itself. It is giving us the notion that whenever we are going to consider the interactions of many, many particles or system of particles, we have to pick the two body reaction first. Then again, another two body reactions. Then again, another two body reaction. That is going on to consider all reactions among the particles. But we have to pick the two body reaction first at once, right? So it is giving by the third law. It is given. Okay. So whenever we are having the two body, so there are many particles, system of particles here. Suppose there are many stars, we are going to consider the interactions between the many stars or various objects in galaxies or any other places. So here you have to pick first any two, then move to other two, then and that is going on. You cannot pick the three body simultaneously. So you have to first two object and two object and two object and two object. And all the things are considered by the inertial observers. Okay. So this is the real meaning of the Newton third law. Okay. So in the next lecture, we will actually see the application of the Newton's laws and how the inertial observers can solve many complicated problems very easily. Okay. So this will be our series, and that will be coming very soon. Okay. So let me end here today.